around 2,580,000 years ago, denoted only by the seemingly insignificant disappearance of calcareous nanofossils such as Discosta pentiridatus, the Pleistocene epoch began. It was here that Earth experienced its last major ice age, the evolution and rise of the human species, and the mass extinction of some of the largest megafauna ever to walk planet Earth. This podcast will cover a brief overview of the Pleistocene epoch, the possible reasons behind the extinctions, and what we can learn from the past in today's current climate. The Pleistocene epoch spans from 2.58 million years ago up to 11,700 years ago, and is currently broken up into 4 ages: the Glacian, the Cambrian, Middle, and Late. It is this final epoch, the Late Pleistocene, that is most well known due to a string of extinction events that caused a 60% reduction in all megafauna. In terrestrial zoology, megafauna include large or giant animals heavier than around 44 kilograms. During the Pleistocene, there had been a great radiation of this megafauna across the planet. From Smilodon fatalis, the saber-toothed cat, famous for its large maxillary canines, to the enormous Megatherium americanum, a huge ground-dwelling sloth which reached over 6 meters tall and weighed in at 4 tons. However, after around 126,000 years ago, at the end of the late Pleistocene, all over the planet, this megafauna started to go extinct. Curiously, these extinctions did not occur simultaneously, but spanned over 100,000 years, with large gaps even between the extinction events of species that lived in relatively close proximity. Furthermore, extinction events were more severe in some continents than others. Australia and South America lost over 75% of their extinct megafauna, while Africa lost only less than 15%.
The two current leading theories behind the Pleistocene extinctions are rapid climate fluctuations and the impact of newly invaded Homo sapiens. The climate of the Pleistocene epoch was characterised by over 50 glacial oscillations spanning the northern hemisphere. Analysis of deep-sea fossils and isotopes of ice cores show that such climate change led to habitat loss and fragmentation through the rise of sea levels, which in turn caused the extirpation of Siberian mammoths. Paleontological data suggests that the spread of Homo sapiens from Africa across the continents coincided with the substantial decline of megafauna. Findings of human hunting tools such as close points at 12 North American excavation sites dating to time of mammoths population decline led to hypotheses that humans hunted large animals to extirpation. Pollen and charcoal records from Queensland, Australia show that the timing of human colonisation and megafauna decline coincided with increased agricultural ground burning. Such habitat alteration may have resulted in the collapse of the ecosystem and ultimately in the demise of the fauna that relied on the vegetation for food. Interestingly, studies tracking changes of human and megafauna populations from North American radiocarbon records reveal that the overkilling and climate change hypothesis may have acted simultaneously. The coup de grace model postulates that climate change reduced the megafauna population and the invading humans provided the killing blow to these dwindling populations.
While many paleoecological studies have primarily focused on investigating the agents responsible for the loss of megafauna, only little attention has been drawn to the impacts that the Pleistocene extinctions had on the world's ecosystem. Some species of megafauna still survive in parts of Africa and Asia and act as the engineers and arteries of our ecosystems by maintaining vegetation patchiness and diffusing nutrients over space and time. However, as the aftermath of the Pleistocene extinctions revealed, their loss likely causes a cascade of detrimental impacts on the physical complexity and productivity of the ecosystem. For instance, mixed rainforests were replaced by uniform sclerophyll vegetation in Australia, and a mosaic of steppe and woodland once found in Northern America and Europe was turned into a uniformly distributed tundra. Because defaunation also resulted in a simplification of the trophic structure of the ecosystem, estimates claim that nutrient cycling decreased all over the planet by more than 70%. Therefore, today's biomes are the legacy of impoverished ecosystems, and scientists are focusing on restoring those ecosystem functions lost with megafauna. At the end of last century, 2 Russian scientists started reconstructing the long-gone mammoth steppe in northern Siberia by establishing the Pleistocene Park. They reintroduced large herbivores to the Arctic tundra and taiga to promote the growth of short grass and the trampling of vegetation. Over time,
Herbivores' activity has already reduced the local soil temperatures by 15 to 20 degrees, preventing in this way the unlocking of greenhouse gases from the thawing of the permafrost.
So direct observations of the crucial impacts that large herbivores have on the ecosystem are also demonstrating how megafauna could be the key player in counteracting the global change stressors that are currently threatening the future of our planet. Trophic rewilding will be the strategy to stop today's continuing declines of large vertebrates and to restore self-regulating biodiverse ecosystems that thrived not long ago. So understanding the past could be the key to the Earth's future.